My title is Multifactor Design of Experiments, DOE, made easy and more powerful by Stat-Ease software. Although factor is a word that kind of associates with process improvement, we also can do work on mixtures using mixture design and optimize formulations. In that case, I call it multi-component design of experiments, but the same idea of doing work in parallel, basically, and detecting interactions of factors that are positive or synergistic, finding out which factors don't work together that are antagonistic. And similarly, for a formulation, certain ingredients will work together better than either one alone. Again, a synergism, or they'll fight each other and be antagonistic. We want to know about that. And rather than taking a one factor at a time or one component at a time approach, using these multi-factor, multi-component design of experiments matrices that are built into the software and all the different tools that I'll be demoing for you. I am not a statistician, but I've been doing DOE for over 50 years and learned on the job working in research and development as a chemical engineer. And I also did quite a bit of work on plant process improvement. At that time, I achieved my certified quality engineering. And then later, I got my master in business administration, the MBA. Now I've taken a full circle all the way around back to working strictly as an engineering consultant after helping to found Stat-Ease, running it for many years. And now I'm at the back arc of my career trying to pay back, by helping people apply these tools. So I'll be talking to you about and showing you version 25 of Stat-Ease software. There's actually two levels that we provide. One that probably most people are familiar with is Design Expert. And that actually started up in the late 1980s. The first package we sold was called Design-Ease, only included the factorial design for process screening and characterization, two-level factorials mainly. And then in the late 80s, we put together Design Expert for response surface methods for process optimization, and then eventually merged Design-Ease into Design Expert. For many years, we were just selling Design Expert. And then our gurus, my son, Hank Anderson, who does the development, is the lead of the team, and Martin Beziner, who came on as a PhD statistician, I think at least 10 years ago, working full-time for Stat-Ease, and is now our CTO and CEO. The two of them, Hank and Martin, came up with this idea of having a wider vision, hence the idea of Stat-Ease 360, that includes a script editor for Python. And this, brings in the entire world of Python. Plus, there's some additional tools in Stat-Ease 360. So Design Expert is totally incorporated within Stat-Ease 360. Many of the industrial R&D that we work with and graduate researchers don't need some of those extra tools, and they would work with Design Expert. But others have, capability of doing Python scripting, or they're using computer experiments, and then they would work with the Stat-Ease 360. So I'm going to demo using Stat-Ease 360 some case studies that show what we can do for factorial design, for response surface methods. These are process tools, and then for mixture design, which is for formulation. And then I'm going to lay out many valuable upgrades that have come in since my last presentation to the Alfasoft user community. So that's my agenda for today. Okay, so again, to reiterate that Stat-Ease 360 contains a full copy of Design Expert software. You don't need to buy both. Essentially, SE360, as we call it, is a pro version of Design Expert. And it really does expand the capability 360 degrees because of the addition of the script editor for Python applications. And then it's also offering advanced tools for computer experiments, as I mentioned, but specifically space filling designs such as Latin hypercube. And then we also have space filling optimal designs. And then we have a way to fit data, especially if it's deterministic, that's called Gaussian process modeling, or GPM. And I'll give you a quick look at that as well. So I thought to begin with that I would open up the software and just show some of the different designs that we have available. For those of you that have not used the software before, this will be new. Those of you that have been using the software, it'll look very similar to all the way back to, probably when we first integrated Design-Ease into Design Expert in the DOS platform. As we shifted into Windows, of course, things became a lot, prettier, but the basic structure of the program has always been the same. And the way it works basically is we've got this tree structure on the left-hand side that lays out various catalog designs for process studies doing factorial design, the regular 2-level, and this has been in here since the beginning with the color coding, which is a 2-level design builder with the white diagonal being the full factorials. And I would oftentimes, as a process developer, ask the chemist to tell me what are 5 key variables that I should study as factors in my experiment. And they would be things like time, temperature, catalyst level, maybe the level of a key reagent. And then I would consider going to a 1/2 fraction, which is shown with a green go-ahead design, because these are perfectly fine for characterizing 2-factor interactions, which is really all you should worry about. 3-factor interactions and above are so rare that it's not really worth trying to design your experiment to fit those. So we take a little shortcut, and I like this one a lot, 5 factors and 16 runs. And I usually would put center points in, which are the mid-levels of things like time, temperature, catalyst level, etc. And I would recommend 3 or 4. I think 4 is better. I took training from George Box, who invented response surface methods, the son-in-law of Ronald Fisher, who developed the 2-level designs. In the 1990s, he had created a quality institute at University of Wisconsin, which is close to my home for the summer, which is in Minnesota. I'm actually speaking to you from my winter home where I'm temporarily staying in Florida, and I'll move down here at the end of the year. It's nice to be at the end of your career and at 60% and be able to work at a distance. So I'll just suggest that as an optimal strategy for a career. Putting center points into the experiment is very helpful, because then basically you're doing an experiment with the standard conditions around which you vary each of the levels high and low. And now I can scale up the agitation, because the chemist will say, keep the stirring magnet running at a certain level. And I just kind of laugh and say, well, I'm going to go to the pilot plant, the semi-works, and eventually a 2,000-gallon reactor. So I'm going to have to kind of recalibrate all these factors, and the 2-level design works beautifully. If you put the center points in randomly located throughout the runs, then you have a nice way of seeing if there's any trends, drifts, decays in the catalyst and things like that. And you get an estimate of pure air. That's just kind of a quick idea of how you would proceed with the tools of DOE. I highly recommend using these 2-level designs. And if you want to go to a screening only, we have these yellow designs that are more fractional, but they're good for screening main effects. So it fits into a nice strategy to first screen and then do characterization if you want to do it in 2 steps. And then finally, we have these red designs. These are for ruggedness testing. It's something used for test method development. I'm a member of ASTM E1169 test method development team. And these are designs that are very good for seeing that when you transfer from the research center to the field, that your system, like a test method, will continue to run. So it's kind of a go and no-go type of thing. But this allows you to put more factors in. You can actually saturate these arrays with 1 less than the number of runs, like 15 factors and 16 runs. Now, in the early 2000s, we recognized that this standard design builder that goes all the way back to Fisher is going to be difficult if you have more and more factors. And with the advent of robots, doing the mixing and 96 well plates, for the biotech, you can do more and more factors, and these designs begin to become too large, even with the fractions. Like with 9 factors, the best characterization design has 128. So our team developed templates that were created from optimal design tools for characterizing with a minimum number of runs, and maybe just one more run in some cases to get an equal number of pluses and minuses, but they're near to minimum or minimum. So we can see that shifting over to these minimum run for 9 factors, we can go down from 128 down to 46. And similarly for the screening with 9 factors, the least is 32. Technically, you can get by with 2 times the number of factors at the minimum for just main effect testing, which would be 2 times 9 or 18. But if you look at this, you'll see that if we select the 18, there's a red or orange warning that comes up. And this is due to our founder, Pat Whitcomb, who was my colleague going back to pre-Stat-Ease days, back to 1974 in process development group. One day he came up, he said, well, I know we spent a year generating these designs, because this was back in the early 2000s with slower computers. But I just can't sleep anymore, because I know when people run these experiments, they'll probably have some mistakes made or have what we call botched runs. So he made us redo the whole thing, which took another year, to add in 2 more runs. And that's what we recommend. So these are really, really valuable tools. I would suggest starting with the regular 2 level. If you get too many factors, then shift down to the minimum run. If you want to first screen, pick that one, or characterize. We can also do multi-level category, because sometimes people say, well, Mark, I've got 3 different types of stainless steel for this artificial knee that we want to develop for implants. And can we do that? Because this was more than 2 levels. I said, fine, we can do that. We can give you a design that has, 3 different types of metals, like a couple of stainless steels, stainless steel 1, stainless steel 2, and maybe titanium. We'll try that. And then these could be other types of things that we want to test, like the dimensions, various dimensions and things like that. So now we've created a 3 times 2 times 2 or 12 run. Now what happens is, if you say, well, I want to do actually 3 of the second thing, and I want to do 4 of the third thing, and I want to put a 4th, category factor in, and I want to do 5 of those, well, now we're getting into, a large number of runs. So at that point, I suggest going to an optimal design, and then just fit a model that'll get the 2-factor interactions, and that'll reduce it down tremendously. In this case, from 180 points down to 61, and this is actually including some additional points to test for lack of fit. I would put in probably some replicates also, like I talked about before for the center points. Now, whatever design you set up, you can do a power calculation if it's a factorial design, which I highly recommend, to make sure that as you cut back the number of runs, you don't reduce the power. And then we'll get into the details of the power, but basically it's a right sizing tool to make sure you don't make too small of a design and miss something important, or on the other hand, make too big of a design and overdo it and generate significant outcome that are not, important. So I'll show you a case study on this 2-level design. And I'm actually going to kind of skip ahead at this point, because otherwise I'll talk too much. And we'll get back to the response surface method tools that we have on that tree on the left, and some of the other tools for mixture design, etc. So while I'm on a roll with the factorial design and going back to the 2-level design, this is something that I like to show, and those of you that already are proficient in DOE, hopefully using Stat-Ease software, can use the same argument to try to convince your colleagues that the 1 factor at a time approach, or OFAD, just isn't going to cut it. Once you get close to where you want to be, you really need to switch over to this multi-factor strategy. Now, this is a study from SKF in Sweden. And Christer Hellstrand, who was one of their top engineers, was learning from George Box in Wisconsin. He flew all the way over how to do better at this bearing that they were trying to improve, and they just couldn't get anywhere with the Swedish engineers. I'm Anderson, so I get this. My dad was a master civil engineer, Jim Anderson, and my grandfather, Harry Anderson, was also an engineer. He did construction work and worked at 3M. So I know that when you're an engineer, you have very strong opinions about things. And perhaps, you know, if you're from Sweden, you might have more, but I don't want to get started with Norway versus at this point. But this is very common, and you come across this with chemists and other scientists. They feel like they can just individually or as a group decide that there's probably one factor. If we would just increase it from the low to the high, we could solve this. And what SKF needed to do was double the life of this bearing at accelerated conditions. Otherwise, they were losing their market to, you know, product from Japan that was coming in. And when they tried it, and this is an actual study reported by George Box, with just one factor, they did get an increase like they expected, but it wasn't double. So they went back and tried a second factor that they didn't think would work as well. Maybe it worked a little bit better, but probably that's just variability, right? Almost certainly it is. And it didn't really come close to doubling. So then one more try, factor C, which did have the advantage. It was actually replacing this plastic raceway. It had been metal before, and if they could switch it to plastic, it would be cheaper. And they were hoping that maybe it would also improve the life. However, it didn't really improve the life, but it didn't hurt it either. So this is an example of a win, because a factor that they've studied doesn't significantly affect the response, but you can switch to the cheaper level. Now, all along when I show this, people I'm sure are thinking, Mark, just look up, because here you can see that there's a big increase in the life, and it's far more than doubled. And of course, this is an example of an interaction of two things. The factor A, which was the oscillation, which is a kiss of the bearing to the cage, and B was actually a heat treatment. And by increasing both of those at the same time, they got a huge increase. So the advantage of the multifactor being the revelation of breakthrough interactions, in this case, a positive one. It could be learning about things you don't want to put together that are antagonistic. That's also valuable. However, although I'm excited as an engineer about these huge improvements that you might find, the other part of it that is of more interest to me as a master in business administration and the research and development directors is because of the parallel processing, we can reduce the amount of time that's spent on these developments by probably about half, from what I've heard from people and what I see in the headlines. And the reason can be explained in terms of equivalent power. Because with this two-level approach, which is a 2 to the 3, we represent this as 2 levels to the power of 3, which is the number of factors, or we have 8 combinations. We're getting 4 at each of the levels of each of the factors. So we have 4 at the high level at the right side of the cube, and sample size 4 at the low level at the left. So we're doing 4 by 4 comparisons. Furthermore, at the same time, we're getting 4 by 4 on B, top to bottom, and C, front to back. And we're getting estimates of 3 two-factor interactions, not only the AB that was active, but also AC, BC, and even ABC, which is very unlikely. Probably any effect from that is just due to error. And we'll actually use some of those high-order interactions in our calculations for the statistics. Now, the OFAT experimenter is stubborn, and they say, well, okay, I can do this, though. I can do 4 at the baseline and 4 at each of the high levels. So then I can just come back to them and say, now, look, you've done 16 runs to get the same 4 by 4 power, and I've only done 8. Now, as you get into process troubleshooting like I did, and you're trying to get in more and more factors, the efficiency just keeps increasing to the point where you'd be crazy to do OFAT. So hopefully either you're already convinced of that and you can use this argument, or you're just getting started on doing DOE. But I think it's really important that anybody doing experiments, knows about these, at least the 2-level factorial designs. And it's very easy to do using the software, as I showed you. Now, all of this comes from a strategy that's very well developed since George Box in 1951 invented the central composite design. And I'll show you in the software that when you get the software, or if you have it already, if you would go through the tutorials, I think you'll find that to be very useful. So we have in the software a nice tutorial on the 2-level design, and I'll give you one case study of that. And then we also have one for the response surface methods, and this happens to be a chemical conversion example. George Box worked at Imperial Chemical, so a lot of work in the chemical industry from the 1950s on with DuPont and beyond using these tools. And here's the layout that Box invented with Wilson. The central composite, it's a cube like the one I showed you for the bearing case, but now we add these center points, which are at the middle, and then these axial points are represented by stars that are going outside of the face. But you can move those into the face of it and create a face-centered central composite. So the idea of screening and characterization, which work from the 2-level designs that Fisher invented, and we would use the yellow for screening or the minimum run resolution 4, which are labeled as screening designs. For the next level, where you're trying to characterize the 2-factor interactions, we'll switch over to the green designs or the white ones, which are the full factorials, or the what we call a resolution 5, sorry for the jargon, which are labeled characterization to make it a little bit easier. And then we add the center points, which I showed you how easy it is to do. And if there is significant curvature and it's important, we can actually augment the original design using tools in Design Expert, or we can start up a new one. And then finally, we do confirmation, and we have tools for that in the software, or you could run one more 2-level design, which would be one of the red designs. And that would be really thorough to make sure that any variations in things like temperature, humidity out in the field, that your system will withstand that. Okay, so focusing on the first part, here's the first case study I've got. And excuse me for a little bit of a focus on chemical reaction, but the same templates can be used for anything, whether it's biotech, food. It could be making bearings, as I showed you. But basically, you identify variables, in this case, feed rate, catalyst level, agitation, temperature, and atmosphere. And this one I like because, it goes back to something I learned, but never actually ran one of these continuous stirred tank reactors, or C-stars we call them. So stuff is coming in, it's being constantly stirred in these kettles, and then it's coming out the other side. So it's a continuous process, but it's kind of a mixture of continuous and batch at the same time. Now, a full 2-level experiment would be 2 to the 5 power, would require 32 runs. This would be too many for one day, so the experimenters considered 2 options. They could split their design into 2 blocks, and blocks are a really good tool to consider, or run the half fraction. And this design does have the center points in it. So I've got this teed up, and here's the layout in randomized run order. And Finn, I'm just going to ping you at this point. Have you been hearing me so far and seeing my screen okay?
Yes, no problem at all.
Excellent. And I know you had a lot of questions before with the prior presentation by Magnus on his tool, but that's a more widely used software, so I'm not surprised there would be a lot of questions. If you hold the questions till the end, that'd be perfectly fine with me, and that might be easier for me to not get carried away here.
Yes, I understand. No problem. I think we will actually have Alfasoft product manager from our Swedish office, Mehmet. He'll take the questions with you. and we'll do that at the end, as you said.
Okay, great. Thanks again, Finn.
Okay.
Okay, so we now have data collected from this two-level design. You can see that it's laid out in random order in our recipe sheet, and then mixed in here, we're going to put some center points just so that you can see a better layout. In the end, I've got data that was done without center points, so we'll work with that. But just to show you some options. So one of the options would be to go to the full 32 run, which should be more powerful. But because they're going to only do 16 per day, we need to go in 2 blocks. And then what I would do is in each of the blocks, I would probably do 2 center points. And one of the services you get as a registered user of Stat-Ease software is you have accessibility to our Stat Help team, where I take point and you can send in a question about a design you're contemplating, and I will give you advice. If it's more complicated questions regarding analysis and the algorithm, I would refer you to our PhD physics and programmer, Joe. And if it's more pure statistical, I would send you over to Martin, our PhD statistician. But these are things that I could speak on. So here we would have day 1 and day 2, for example. This could be 2 different reactors side by side, 2 different lots of raw material, or all of the above. We did the power calculation. In this case, I wanted to detect at least a 3% difference. If it was less than 3%, the experiment would not be a success. I would like to get a lot more than 3% in the yield improvement, but 3 is at the minimum threshold. The normal variation of yield, if we run these reactions over and over and collect that data and calculate standard deviation, is 2. And so we can see that the power is very good. In fact, probably more than what we need. And then this would be the layout with the 32 run option. And then embedded in here, I've got some center points. Well, I think I ended up with more center points than I wanted to. So you can easily just go back around again. And we could shift the number of center points down to some lesser number if we wanted to. But in this iteration, I'm going to go back to a different idea, which is to do just 1 day's worth and do the 1/2 fraction. And then I would suggest doing 4 center points. And so now, as far as setting these up, it's just a matter of typing in the names, units, the types of factors. Now, the last factor is whether we leave the reactor cover open or closed. And if we close it, we're going to purge it with nitrogen. If we open it, then the air is going to get in, which probably isn't good. But to save time on closing the cover, they thought maybe we would try not closing the cover. And so this one is a categoric factor. And this is why we got the proliferation of center points, because we're doing center points for both categories without the cover, letting the air in, and with the cover. So center points, in this case, you have to manage a bit. Now in this 1/2 fraction, of course, the power has gone down, but it's still pretty good. And so here's our design layout in the second iteration, which is the idea of just doing a 1/2 fraction. So that's what they did. They got tired of dealing with center points, so they just took them out, which is not the ideal, but so it goes. And now we have the yields, and we have the ability to easily sort and see that we're getting some really good results. And so now I would suggest you use our custom graph features and kind of at the very least, do some work to look at the main effects. And we see that catalyst has a really big effect. Positive, it's red and high correlation, and temperature also to some degree. But what this only shows us is main effects. There's probably interactions because it's a chemical process. So we now use the superior tools of graphical selection that DOE-dedicated Stat-Ease software offers. And this is something that you can pick up through the tutorial that I mentioned, but you can easily be like an American cowboy and lasso these effects that are off to the right that stand out. And so these are going to be the effects that we're going to pick for our model. And so here again is the way that we pick effects is we should be able to drag over. And now we have identified a vital few number of effects. Some of them are interactions. And at the same time, on the right side, we get this very useful ordered bar chart that I really like to present if there's, non-statisticians in the group or people that are not familiar with the half normal plot. This Pareto chart is a lot more user-friendly. There's a couple of limits shown here. Most people know about t-value, and then this red line is pairwise corrected, which is more rigorous at p of 0.05. But all of these are well above it. The other effects that we didn't pick will be used as error estimates in this unreplicated factorial. We had center points, we could estimate pure error, but we don't have those now. And then simply, going through the p-values, making sure your predicted R-squared is good. I would copy out this coded equation, which is quite easy with the software for your report. Always check diagnostics to make sure the data are normal using this normal plot of residuals versus run to make sure there's no outliers outside of the red lines. And then we have a very useful plot also invented by George Box, in this case with Cox, that will tell you if there's a need for a transform. In this case, no. Now we can use the superior tools of Stat-Ease software to graph the results, and we have, some very interesting interactions where the effect of one thing depends on the level of the other. Catalyst level will, if you increase it, will have much more of an impact if you have high temperature at the 180, for example. We can also look at this in contour view, which gets us into the response surface methods, and then 3D surface, and we can see that there's, some kind of a peak up here. All right, and then our numeric optimizer, which can work on multiple responses, does a hill climbing search, and I always recommend using this. And I would say to my client, what do you want at the minimum for your yield? And let's say they say, well, it's got to be at least 70. And how much would you like to have? Well, of course, 100%. And then the program does a hill climbing search, and I like this ramps view because you can see at a glance that certain factors like A and C over the range study didn't have an effect. But if we get the catalyst increased, the temperature increased, and then use nitrogen blanket, that'll be our best result. Last but not least, I suggest that you take your optimal conditions that you've found, and you do at least 3 follow-ups. I recommend 6 even would be better. And then as you follow up, you can make sure that this is going to work as you come back to the process later with these new conditions. And hopefully, we're getting really high yields, in the 90, even 90 plus range. It'll vary. And as long as this result is within this range, you're good. If a new lot of raw material came in, like it would do with General Mills chemical using natural materials, and something was different about it, and now our yield is dropping way off, well, then it would turn red, and we would have to go back to the drawing board, get the chemical engineers, the chemists together, and see if we could figure out how we can recalibrate this reaction to get it back up to where we need it. So that's a demo of the 2-level design. And here is the result. It's especially important to get the catalyst level up and the temperature at the same time, and then do it under the nitrogen blanket, and then we can get over 90% yield. So it was a real big breakthrough. All right, well, that's the main bulk of what I wanted to cover in my presentation for demo purposes, because the 2-level factorial are the core of DOE. And they're really, really good for any type of process or some kind of, it could be mechanical production, like the bearing, The two-level design is always going to give you the most advantage. And if you go to the fractional designs or even go to the screening yellow designs, sometimes you can hit a home run, as we say in US. World Series is coming up for baseball straight away at the first time at bat. These minimum run designs are very helpful, especially I would say more so for the screening. I would probably use them, but you could use them to characterize for more factors than you would realistically with the standard two-level designs. Now the response surface methods. I have a little story to tell you there. So when I worked at General Mills Chemical and I learned about these tools of design of experiments and response surface methods, these were early days. We didn't have Stat-Ease software back then, but we used our experience to develop Stat-Ease software. Pat Whitcomb, with my input and some others from General Mills Chemical in 1982, came out with the first package. 1985, we incorporated, and thus we're celebrating our 40th anniversary of incorporation. But back in the day, my PhD chemist, Bill, and I were tasked with improving the yield of natural vitamin E derived from soybean oil. And Bill was very strong at one factor at a time. So Bill said, I'm pretty sure that factor A is going to be the key. So I'm going to do a series of runs at many different levels, and I'm going to, draw a curve. And we might have actually used graph paper and a graphical tool we called it the snake, that you could bend and get it to go through the points and then take a pencil and draw it out. It might have been like that he used this, and he said, look, Mark, if we set factor A at a certain level, we're going to get pretty high yield. And now I'm going to then set factor A, and I'm going to look at one more factor that I think is also going to have an impact, but probably not as much. And we'll set that. So then I said, Bill, this is great, but I just learned about a new tool called response surface methods. And it turns out that as long as you do at least 3 levels of each factor, we can fit a higher order polynomial model. So I'm going to do a 3 to the 2 design, which is 9 runs. I'm going to add 4 center points. And on this layout here, I can draw in my design with these red dots. And then in the middle, I'm going to do 4 of those in a randomized plan. And from this experiment, even back in the day, using timeshare services with regression modeling, we could fit a predictive model that had not only the main effects, x1 sub x2, and the interaction, which you can get from the 2-level design, but also squared terms. And with this, then, we could draw out, and this is obviously done much later using more modern day software from Stat-Ease. We can see that there's a rising ridge. And I can get from a little over 80, I think, that Bill had, up to 95%. And that difference is worth $2 million a year. So the president of the company came to the research center to congratulate me and give me a $2,000 check, which I always like to think about that. But back in that day, I was pretty happy to get the recognition and the $2,000. So these really work, and what I would suggest, going back to the tutorial that I showed you before for response surface methods, is if you would go through this, and you can download a trial of our software if you don't have it, and you can work through the factorial design tutorial and this response surface method. And then associated with these tutorials are files. So cutting to the chase, here's the file that is associated with the tutorial. It's very easy to set up these response surface methods. We have this tree structure on the left. So now we're going to progress down from the factorial to the next level, which is response surface. The standard central composite. We also have Box-Benken designs, which is another George Box thing with Benken that has only 3 levels of each factor. And then many people like to go straight to the optimal custom design, and that allows you to get all kinds of things done, higher order polynomial fits, multilinear constraints, and things like that. So very easy, again, to select a design with some advice from our stat help team if you need it, or within the software, there's lots of help and advice, or other resources, available on our website, various YouTube videos, case study write-ups, and then some textbooks that I'll show you later that I would recommend, if I do say so myself as a prime author. Once you put in the names and levels of the factors, and in this case, blocking it across 2 different days, you can do many responses, you get your recipe sheet, and then you run the experiment, and you collect the data, which again is, in this case, available from within the software. And now the data are collected. You can do some graphing of it, but with the central composite, it's a little bit weird with those points sticking out of the box on either side. So I would say just go straight in and do the regression. The program will suggest to you, in this case, we designed to fit a quadratic model, and a quadratic model is suggested. And if you notice that there's some p-values that are high, above 0.1 in particular, you can do a model reduction. I like doing it from the full model and taking out terms one at a time that are above 0.1. And I like doing this to reduce the model. Time is not significant, but it's there to support the hierarchy because it's part of the AC term. So there's some various catches in the software to make sure you don't create what's called an ill-formulated polynomial model. Diagnostics, and then we get a more interesting surface because we've got these squared terms in it. So now we're going to get some curvature in the system. And this is kind of like that rising ridge I was showing you before. Now the second response turns out that you can fit without having those second order interaction or squared terms. So we're going to follow what's called the principle of parsimony for regression modeling, which is keep it simple, but not simpler than possible. That was a saying from Einstein. Now in this case, we see that there's really just has the main effect of time and catalyst. We could take temperature out of it, but I'm going to leave it there. Check the diagnostics. And now this will just be a planar surface. If it was a two-factor interaction model, it would be twisted. If it's got square terms, it'll have curves in it. So we now have the makings for a multiple response optimization. And in this case, we could go back to the tutorial and see what the goals were, but I'm just going to say, let's say we're trying to get at least 80% on the yield for the conversion. We would want to get 100%. And let's say activity is a product quality attribute that we want to target. The beauty of this is it's a what if situation. We can meet with our client or with our product manager if we're within the company, and we can find out what the target really is. And if they said, well, it's 63, I would like to hit it exactly on target, then you would say, well, give me a range to work within because I need to have some flexibility to get everything you want. So let's say 60 to 66. And then you can see that it dials up after doing a search, the most desirable combination of the time, temperature, catalyst for both the conversion and the activity. Now we could say conversion is very valuable for natural vitamin E, and so we're going to make this more important. And if we did this, it might cause you to go off target, but it didn't actually make a difference. We do have some slack within activity here so that if you say one thing is more important, like the conversion, we might be able to contend with that. And then I like to finish up these response surface methods with what's called a graphical overlay. And in this case, time and catalyst were a very important combination. We saw that for the conversion. So I would put those as our axes for the overlay plot. Here's our window. And then if the design is large enough, oftentimes you can get a more conservative sweet spot still by superimposing a confidence interval around the outside. And this is actually what's called a one-sided confidence interval. But now we have a more conservative window. This approach is quite good for pharmaceutical development to get quality by design space. And it can be very helpful to assure the European regulatory or the FDA that you can consistently make good product. Okay, just pinging back to you, Finn. So far, so good?
Yes, everything is perfect.
Excellent. Okay, then last but not least, I want to talk a little bit about mixture design. In this case, the factors are ingredients of a mixture, such as this milkshake that this young lady maybe is enjoying. We're not quite sure by her look if she likes it or not. And the response is a function of the proportions, not the amounts. So, like Shakespeare said, just a taste of the ox will do. You don't have to eat the whole ox. So she doesn't need to drink that whole milkshake, but if she did, we'd probably think that was pretty good. But she might take a little sip and make a sad face because it's the proportions of the milk fat, the sugar, chocolate, things like that, that's going to make the difference. Now, to make it more feasible, we're going to fix the total also, which typically is going to be 100 weight percent. But it could be something less than 100 weight percent, or it could be volume. In this case, the total would be just simply one glass, for example, and we could fill it up with either milk or chocolate milk or things like that. Now, this was a tool that was developed back in the 1950s. So this came after Box and Wilson in 1951 for the response surface methods. And basically, it's a conversion of response surface methods that Chaffee developed that fits within these considerations. And you actually shift over from a square space to a triangle space. This was something I thought was the most fantastic thing in my material science class, which was my co-major at University of Minnesota, because once you know any two ingredients, the third is fixed. So we looked at stainless steel and we considered a total of 100 weight percent. And then if you get just the right combination, you'll get what you want. There's a bunch of different regions here that are different types of metals. It's kind of mysterious in metallurgy, but if we go 18% of the way up from the bottom to the apex, which is 100% chromium, we draw a line like this. Now we put in a certain amount of nickel. It turns out that 8%, which is going from the left side to the right side. Now notice that I've got two lines that forms an intersection, and we can simply read off in the third direction, which is going to the lower left for the iron, what that amount would be. So in other words, once we know that we've got 18% of the first metal, which is chromium, and 8% of the second, which is nickel, then to add up to 100, this has to be 74%. So we program this into Stat-Ease software. And so now, for example, people in biotech, let's say these pharmaceutical experimenters that are trying to work with some new commercially available synthetic medias and see if they can maximize the peak viable cell density, can do this via a mixture design. And we have lots of different tools available for the mixture side, including optimal design. Oftentimes mixtures will end up being optimal. This one's an example of what's called a simplex design that can go all the way from 0 to 100% essentially. So we can use all of each individual media, or maybe a binary blend of the two of the three, or all three parts. And we have a specialized design that you can learn about by reading some textbooks. I'll give you a list of them that I wrote, but there's other ones out there. Or you can go do the tutorial on the mixture design, which in this tutorial still fits the triangular space, but they've actually worked within a subset of ingredients on this detergent case where they're trying to hit a certain target viscosity and keep it from getting too cloudy or turbid. And this is a picture of the triangle. The dots show where you're putting these points at the corners, at the midpoints of the edges, at the overall centroid, and then there are what are called check blends in between. So all of this is pretty much set up by default, but you can decide, what order polynomial model you want to fit. With 3 ingredients, I think special cubic would be a good one. Again, you can get advice from from me and our team once you're licensed. And then we create a design that covers this space, create a randomized recipe sheet, collect the results, and then we're going to fit a specialized polynomial model. And basically this is similar to response surface methods, but the model looks different. It doesn't have intercept, it doesn't have squared terms. So you need to study that a little bit to see how it works, but it actually is geared very nicely to mixtures. So if you're working with a formulation, I highly recommend using Stat-Ease software and using mixture design and making sure that nothing is abnormal via the diagnostics. And then we get these response surfaces within the triangle. And in this case, there's a big advantage to using all three of the medias to get the highest VCD, which we can search out using our optimizer tool, putting a stretch target at the top and asking the clients or product manager what you want at a minimum, and then you create an answer. And then do the confirmation. And we can round off these, let's say we're going to use 42% of media one, 22 of the other, and then the program makes sure this adds up to a total of 1. So the media 3 has got to be at 0.36. And then I would recommend doing 3 to 6 confirmations, and hopefully it fits within the prediction interval. Okay, well, what's new and what's in it for you in V25? I would suggest that you would follow this link, or you can go to our website and find it fairly readily. In here, then, you can see there's what we call the full change log, and we just released a minor update to version 25 on October 8th. So if you have the software right now and you haven't installed this new release, I would do it. There are certain issues that are fixed, and so I guess we call these maintenance items. There's always some things, but this one actually does have one new thing, which the import data table now allows renaming of blocks, groups, and subgroups. Okay, then you go back and you can see there was a 0.03 maintenance release, a 0.02, and then the release of 25 was on May 20th, and now this gives you the major features that were added with version 25. And then going back further, you may be using version 13, for example. If you wanted to see all the improvements since version 13, you can go back through this list and you can see 23.1 release December 16th and added the Sturban-Watson statistic. And then version 23, which is where the Gaussian process models got added, the Python script editor, and things like that. So now going back to our software, I just want to mention, I really like in version 25, the new perceptually uniform color maps that remove false anomalies and improve areas of contrast. It's pretty cool. So I'm just going to bring up the software and close out what's currently here. And a couple of things I want to point out. One is that this is Stat-Ease 360, which is a superset of Design Expert that adds this Python script editor, and you can actually see some sample scripts under help. For example, for a Weibull regression, which is used for life testing. But you can create your own script. So if you're conversant with Python, this will really add the utility. The other part of it is that we have in 360 these space filling designs. I mentioned Latin hypercube. There's also optimal distance. And then there's the Gaussian process modeling. Again, a tutorial would be helpful to follow through on Gaussian process modeling. We have a simulation of a gas station, and you're trying to figure out changing the configuration of the gas station, how that's going to affect the waiting time. And it's a function of the tank size and the pumps and some other things. This is a picture of a Latin hypercube, which has 1 point in every row and 1 point in every column. 1, 2, 3, 4, 5. I think there's a 10 by 10. You can specify that when you set it up. All right, and then we have the specialized model, the Gaussian process model. So I'll bring that up. And that'll be the last thing because we're almost out of time. So we have tutorial data for the gas station. So this would be done on a simulation, and the results that we see here are deterministic. So looking at the average waiting time, we could do a standard linear regression, which wouldn't be a bad idea. We'd probably have to upgrade the process order, though, which we can fit because we've got a 10 by 10 grid. I probably would go to the quartic. Now, these p-values don't really mean anything because it's deterministic, so it's really showing the fit. And so here's a picture of what it would look like using a standard ordinary least square polynomial, and you can see it doesn't quite fit exactly, but it fits pretty good. But if you want to get an exact fit, then you're going to use a Gaussian process model. There's various smoothing parameters and other things you can change on it. But this is what it would look like. And this is using the default, which is this one right here, of the perceptually uniform color map. It eliminates some of the artifacts that say around the yellow, for example, that you would see otherwise. It's kind of hard to tell, but there's a difference. And the other thing I like about our new gradient tool is that if you're colorblind, there's an option to do something that's, you know, compatible with color blindness. So do go back and look at this changelog if you're interested to see what's new. And if you're not using the software yet, please, you know, give it a try. You know, going to our website, you can go to the trial point and you can download a fully functional trial for a period of time. I will contact you and you can get back to me. Let me know what you're up to and I can help you. And if you need an extension, I'd be happy to ask our staff to provide that.
Perfect, Mark. Thank you for your presentation. That was great.
Yeah.
We do actually have some questions, but we're running out of time, so I think we'll have to take those in the back end.
Okay, that's
and
fine.
we will send out a follow-up email to everyone with questions and answers. And we will also include a recording of this webcast.
Yeah,
and also,
one more thing is just that we have this December workshop coming. Got to throw that in there. Sorry, I'm right up against the wall, but and then the books. That's it.
Okay.
Thank you.
Thank you. So last thing I want to mention before we go to the next webinar is that there is a materials button on the top right. You can click there for more information regarding Stat-Ease. Yes, there is at least one PDF there. So thank you, Mark. Thanks again.
You're very welcome.
I hope to see you again next time.
Okay, sounds good. Take care now.